So if you work with people, you're working with data. It's just a fact. But here's the big question. How do you tell the story of thousands of people when you can only talk to, say, a handful? How do you possibly bridge that gap between a small sample and the big picture? Well, that's exactly the puzzle we're going to solve today. And the key is a really powerful idea called the sampling distribution. I mean, this is the core dilemma, right? It feels a little impossible at first. How can you be so sure that your little group of 50 isn't just kind of weird? How can their experiences really reflect the reality of 50,000 different individuals? This uncertainty, this natural variation, is what statisticians call sampling error. And figuring out how to handle it, well, that's pretty much the whole point of inferential statistics. To get our heads around this, we're going to start with a thought experiment. It's a what-if game. So instead of focusing on the one sample we actually have, we're going to imagine what would happen if we could take every possible sample we could ever dream of. I know, it sounds a bit abstract, but trust me, this what-if scenario is the key that unlocks everything else. Okay, to make this super concrete, let's forget about 50,000 social workers for a minute. Let's pretend our entire universe, our whole population, is just these three little balls. Simple. We can easily figure out the true average, or the mean, of this population. It's just 1 plus 2 plus 3 divided by 3, which is 2. Easy enough. We know the absolute truth in this tiny world. All right, now for the experiment. We're going to reach into our population, grab a random sample of 2 balls, and find their average. Let's say we get a 1 and a 3. The mean is 2. Great. Write it down. Put the balls back. That's important. And do it again. This time, maybe we get a 1 and a 1. The mean is 1. We just keep doing this over and over and over again, building this long list, not of individual ball numbers, but of sample means. So after we do this 1,000 times, we step back and look at our list. We've got a whole bunch of 2s, some 1.5s, a few 1s, maybe some 2.5s, and we realize, wait a second, we've created a totally new set of data here. This new collection of statistics has its own shape, its own center, its own everything. And that new set of data, it has a name. It's called a sampling distribution. That's the official term for it. It's the distribution not of individual people or scores, but of a statistic, like the mean, that you get from every single possible sample of a certain size. It's the logical bridge that connects our one real-life sample to the population it came from. And here's where it gets really cool. When we plot all those thousands of sample means on a graph, something amazing starts to happen. They form a predictable, symmetrical, bell-shaped curve. What's wild is that even if our original population of balls was kind of lopsided, the distribution of the sample means almost always tends to look like this normal curve, and it's centered right around the true population mean we already knew was 2. So let's be crystal clear on this, because it's the #1 point of confusion. A sampling distribution is a collection of statistics, like thousands of different sample averages. It is absolutely not the same thing as the distribution of individual scores from the one sample you actually collected for your study. It's a theoretical tool that helps us understand how our one sample statistic is likely to behave. Okay, that's a lot of theory, balls and thought experiments, but why should you actually care? Well, as a social worker, this concept is basically the foundation for proving that the work you do actually makes a difference. Let's connect this to the real world. Think about it. Every time you evaluate a program, you're using a sample of clients. The sampling distribution is what allows us to figure out if the improvements we see are real or if they could have just happened by random chance. It's how we estimate the needs of an entire community from just one survey. And it is absolutely how we prove to funders that our intervention had a statistically significant impact. It's the math behind our evidence. So if the sampling distribution shows how much our sample mean might bounce around from one sample to the next, it would be really helpful to have a single number to measure that bounciness, right? A way to put a number on the precision of our estimate. And guess what? We do. That measure is called the standard error. It's really just the standard deviation of the sampling distribution. Think of it like this. A small standard error means most sample means would be packed tightly around the true average. That means our estimate is precise and reliable. But a large standard error means the sample means would be spread all over the place. Our estimate is a lot more wobbly and less trustworthy. And what's the single best way to shrink that standard error and get more precision? Simple. A larger sample size. I mean, this is pretty intuitive, right? A sample of 10 people is going to be way less stable and more likely to be an outlier than a sample of 100 people. A larger sample gives you a clearer, more stable picture, which means less variation between potential samples, and, you guessed it, a smaller standard error. Now, this connection between the sample size and the shape of the sampling distribution is so important, so powerful, that it gets its own special name. It's honestly one of the most fundamental ideas in all of statistics. It's called the Central Limit Theorem, and honestly, it feels like statistical magic. It says that no matter what your original population looks like, it could be skewed, flat, totally bizarre, the sampling distribution of the mean will always be approximately normal as long as your sample is big enough, which is usually just 30 or more. It literally finds order in potential chaos. This is our superpower as researchers. Because we know the sampling distribution will be a normal bell-shaped curve, we can use everything we know about that curve to make statements about probability. This theorem is the reason we can confidently use some of the most common statistical tests, like t-tests and z-tests, to figure out if our results are actually meaningful. It is the engine that runs almost all of statistical inference. Phew. Okay, so we've covered a ton of ground here, from a tiny population of 3 little balls all the way up to the superpower of the Central Limit Theorem. So let's just take a breath and boil it all down to the key things you really need to remember. All right, here are the big 3. First, sampling distributions are all about how a statistic, like a mean, would vary if you could take a ton of different samples. Second, the standard error is your go-to measure for precision. You always want a smaller standard error. And third, the clearest path to a smaller standard error and a more stable result is a larger sample size. It's as simple as that. Ultimately, it really all comes down to this one idea. The sampling distribution is the crucial link. It's that logical leap that lets our one small sample speak for an entire population. It's the very bedrock of credible, evidence-based research. So the next time you see a study's findings, you'll know the real question isn't just about the data they found, but how that one finding fits into the whole universe of possibilities.